Hello and welcome back to GCSE Science Simplified. In the last episodes, we explored electromagnetic induction, how moving a magnet near a wire can produce a current, and how generators use that idea on a large scale. Today, we're taking the next logical step. How do transformers change the voltage for electricity? And why does the national grid do this on purpose? By the end of this episode, you should understand how transformers work, what step up and step down transformers are, and why high voltages are used to move electricity around the country safely and efficiently. Let's get into it. Let's get a quick reminder about induction, as it's fundamental to how transformers work. A potential difference is induced when a magnetic field changes near a conductor, usually a coil of wire, and the size of the induced voltage depends on how strong the magnetic field is, how fast it changes, and how many turns the coil has. And the key principle? The induced magnetic field always opposes that change that caused it. That principle sits behind everything we do today. Let's build a model you already know. Think about transformers. You know, the robots, Autobots and the Decepticons. They can change from a robot to a car, then back to a robot. Electrical transformers are similar and different. Here's the model. An alternating current in the primary coil is like the robot form. This alternating current creates an alternating magnetic field in the iron core. This is the vehicle mode. Then the secondary coil of the transformer, that alternating magnetic field, is then turned back into alternating current, returning it back to that robot mode again. So the flow, alternating current, turns into a changing magnetic field, which changes back to alternating current again. Just like an Autobot, turns from a robot into a car and back to a robot. Nothing travels directly from one robot to the other. The change of form carries the message. In the same way, no electrons from one coil of the transformer transfer to the other. Energy is passed through the changing magnetic field in the iron core. And just like the Transformer films, the change only happens when there is reason to do so. If the current were direct current, nothing changes, so no transformation occurs. That is why transformers only work with alternating current. We'll keep returning to that model as we go. A transformer has three key parts: a primary coil, a secondary coil, and a soft iron core. How does this work? Well, an alternating current flows in the primary coil. This creates an alternating magnetic field in the iron core. That alternating magnetic field passes through the secondary coil, and because the field is changing, a potential difference is induced in the secondary coil. Energy has been transferred, but through form changing, not by electrical contact. So, what happens then? Well, the size of the voltage depends on the number of turns on each coil. Here's a simple rule. More turns equals more induced voltage. So, if the secondary coil has more turns than the primary, the voltage is increased. This is called a step-up transformer. If the secondary coil has fewer turns than the primary, the voltage decreases. This is called a step-down transformer. And remember, these transformers only work with alternating current because the transforming relies on that magnetic field constantly changing. So why does the national grid use transformers? Right, whenever current flows through a wire, we know some energy is wasted as heat because of the electrons colliding and causing friction with the ions in the wire. The key rule is this heat loss is mainly dependent on current, not voltage. Try this. Rub your hands together slowly. Now, not much heat with that low current. Now rub them together much faster. Much more heat is generated. This is the same for a faster current. There's more friction. So the national grid uses transformers to keep the current low and keep the wires cooler, not wasting energy. Here's the journey electricity takes. Power stations generate electricity. A step-up transformer increases the voltage to very high levels, often hundreds of thousands of volts. This means the current needed is now much lower, reducing heat loss. Electricity travels long distances through these transmission lines. Then, near homes, schools, hospitals and workplaces, step-down transformers reduce the voltage to safe levels. That's 230 volts in the UK. So, step-up transformers take high voltage, low current and have efficient transmission. Step-down transformers make lower voltages, which is safe for local use. Transformers allow us to move large amounts of energy efficiently and safely across the country. Even though transformers change voltage, they do not create energy. Power in equals the power out. Now, we know from our electricity topics, power equals voltage times current, so if the voltage increases, the current must decrease. If the voltage decreases, then the current must increase. Just like a transformer robot changing shape, the total robot is the same, just in a different form. Energy is conserved. Always. Here's some quick recap questions. Try to mentally answer these while you're listening. Pause, go back to them if it helps. Why do transformers only work with alternating current? What role does the iron core play? What is the difference between a step-up and a step-down transformer? Why does the national grid use high voltage transmission? If the secondary coil has more turns than the primary, what happens to the voltage? Now, feel free to go back and listen to parts of this podcast again just to help you answer those, but good to get you thinking. So today we've learned transformers work by switching energy between electrical and magnetic forms. Alternating current gets turned into an alternating magnetic field, which induces an alternating current in the secondary coil. Changing the number of turns changes the voltage. The national grid uses high voltages to reduce the heat loss, making it more efficient. Step up is transmission around the country. Step down is for local supply, keeping us safe. And energy is always conserved. Thanks for listening to GCSE Science Simplified. Please share this episode with someone revising the same topic and keep learning.